Okay, we're going to talk about section 2.6 where we're analyzing rational functions. Rational functions take this format where there's a function on top in a fraction and a function on the bottom, and so they take this format, this structure. G of x obviously can't be 0. You can't divide by 0 in a fraction. Okay, so the key concept about rational functions that you need to understand is that when the values that make the denominator 0 are most often going to create vertical asymptotes. There's one special case where they won't create a vertical asymptote, but regardless, even in that case, the values that make the denominator 0 will not be in the domain of the function. Okay, so for example, if I have 1 over x minus 4, and I take a look at the graph of 1 divided by x minus 4, you see that there's a break in the graph here, and that break is called a vertical asymptote. Okay, there at 4. We can figure this out algebraically by taking the denominator and saying, okay, where is that thing 0? That's going to tell us where the vertical asymptote is, and it's going to tell us what value can't be in the domain. And so we can see that it's at 4. The denominator cannot be, or sorry, x cannot be equal to 4 because it makes the denominator 0. So if we want the domain of this function, then it would be all real numbers. X cannot be 4. Okay. We could also write this using interval notation. So we could write that the domain is from negative infinity to 4, not including 4, and then from 4 to infinity. Let's look at another example that's a little bit more complex. So here I have a rational function. I'm trying to find the domain, and I have the same principle is going to apply. I want to figure out when is the denominator equal to 0. Okay, and this is a quadratic, and so you can use the magic x to factor it. What you'll find is that you get x plus 3 and x minus 2 when you factor it, and so you get that so you get vertical asymptotes at x equals negative 3 and x equals 2. We can take a look at this graph real quick. So we have x minus 5 in the numerator, and in the denominator we have x squared plus x plus 6 minus 6, Okay, and so the graph here, you can see has 2 vertical asymptotes. There's a break here at negative 3 and also at 2. You can also see this in the table. So if you go to your table and you go to negative 3, you see an error there. So that's not going to be in the domain. And you see an error there at 2. So that's not going to be in the domain. In order to write the domain then, you could say, you could write all real numbers. X cannot be negative 3 or 2. You could also write from negative infinity to negative 3, negative 3 to 2, and then 2 to infinity, all with parentheses. We're trying to find the domain on this one. Again, the same principle is going to apply. And I just realized that I actually put the graphs down here for all of these, but anyway, we'll use those in a second. So x squared plus 3, when is that equal to 0? When you subtract 3 from both sides, you get x squared equals negative 3. When you square root both sides, you get x equals square root of a negative number, right? Plus or minus. Okay, if it's square root of a negative number, then there's no real number that will make the denominator 0. So this function has a domain of all real numbers. Or you could write negative infinity to positive infinity. Okay. Down here, I have the graphs of the functions up above. You can see a vertical asymptote here at 4. When you're asked to write a vertical asymptote, you write it as x equals 4. Here we have a vertical asymptote of -3 and here at 2. So we write x equals -3 and x equals 2 for the vertical asymptotes there. Here's the graph of the function, the third function there. You can see that this has no vertical asymptotes. It's got sort of just a dip there, and then it kind of flattens out. And so this one has no vertical asymptotes. So that's vertical asymptotes. There are also something called end behavior asymptotes. Sometimes they're called horizontal asymptotes, but they're not always horizontal. So that's why we're going to use the term end behavior asymptotes. Okay. There are 3 situations that you will encounter with end behavior asymptotes. Okay. Situation 1. So by the way, we're only addressing rational functions. Again, that's functions that look like this. Situation number 1. The degree of the numerator is less than the degree of the denominator. Okay? And so an example of that might be something like y equals x over x squared, x over x squared minus 1. Okay? So the degree on top is 1, the degree on the bottom is 2. So the numerator is less than the denominator, and so that one will have, those functions will always have an end behavior asymptote at y equals 0. Okay? We can see a situation here with this first curve, 1 over x minus 4. And in that curve, we have an end behavior asymptote. In other words, if we look at the end of the graph to the right and to the left, you can see that it flattens out to y equals 0 there. Situation number 2. The second situation we'll look at is when the degree of the numerator is equal to the denominator. All right? And in that case, we're going to look at the ratio of the leading coefficients. So ratio of leading coefficients. Okay. What's an example of that? Well, we have one right here. This third function here. You see the degree on top is the same as the degree on the bottom. So the end behavior asymptote would be at the ratio of the leading coefficients. So here's the leading coefficient on the top, it's 1. Here's the leading coefficient on the bottom, it's 1. So the end behavior asymptote would be at y equals 1. Okay. Here's the graph, and we do see that at y equals 1, the graph approaches that at the ends. So the graph gets close to y equals 1 at the ends of the graph, to the left and to the right. Therefore, y equals 1 is the end behavior asymptote. The last situation is if you have the degree of the numerator greater than the denominator. Okay, and in that situation, you have to divide the polynomials to figure out where the asymptote is. In that case, you might have a slant asymptote, which would be an asymptote that goes like this. It's not horizontal. You could have a parabolic asymptote. You could have all different kinds of asymptotes. And you will just find that asymptote by doing the division. Okay? And whatever your quotient is, that's where the asymptote is. And that's pretty much it for end behavior asymptotes and vertical asymptotes and domain of rational functions.